Morning, everybody. Morning, Donnie. Morning, Nikolai, calling me Meg. Morning, Ryan. Morning, Hike. Morning, Azra. Morning, Charlie. Morning, Rainy. Hi, Ava. Anyone else who's watching, good morning. So, today's agenda, I kind of changed it up a little bit. Daily posts, kind of, I don't know, they're a little unwieldy. They get a little long. So, better late than never. I tried posting a picture, make it a little more virtual, a little more like the classroom. So you click that picture right there, Virtual Classroom 526, and the agenda's in there, with links to YouTube, with links to Remind, so I don't have to type all that out. Morning, Josh. So I have my fun fact there. That's not a DNA. There is no DNA. We're done with those. Alright. It's blocked? That's weird. I will pull it up for you then. So here's our classroom. Hi, Sam. On the agenda today, we are going to... I'm blocking out a class pet. Spirit Rover. We're going to discuss this clock that was blocked, according to Hike, and the geological timescale that goes with it. It's part of the fun fact. Just quickly. And then go on to reviewing the layers of the Earth, their different characteristics. What are some major things you should have researched when you were doing your research last week in the Explore section, and then answer the Explain questions in Scratching the Surface. Scratching the Surface is going to be due Thursday before midnight. And I think we will be fine for that deadline. I'm sorry, Autumn. I'll have to find a transparent background version of them. So you can check that out. Agenda's in there. Also, for those of you that need it, you can click the Remind button, and it'll pull you up to Remind. And you can click the YouTube button, and it'll bring you to the channel. Okay? I know I don't have a Newton's Cradle. I couldn't find a transparent background little Newton Cradle. I will keep trying. I appreciate the tips. I'll look for more things to add or change it up. Alright. So, fun fact number 4. Evidence from radiometric dating. That means we are looking at isotopes, radioactive isotopes. Remember, an isotope is a different form of an element because it has extra neutrons. And when it has extra neutrons, those atoms usually become unstable and they give off more energy. And that's radiation that we talk about. So we talked about this when we talked about the Seuss effect and evidence for human-caused climate change. Right? We talked about isotopes of carbon and carbon dioxide. In this case, we're looking at radioactive elements in the Earth's crust and down below into the Earth's, maybe even to the upper mantle. Indicates that based on its radiation and its half-life, the Earth is about 4.5 billion years old. The Sun is about 5 billion years old. Okay? The geology or deep time of Earth's past has been organized into various units according to events which took place in each period. And so then I posted a picture of a clock. And this clock, and if you read it like a clock, you go clockwise around, tells you the different periods of Earth's past. So I'm trying to show you where humans are versus all these ancient epochs across the Earth. So Zoom in a little bit. This is millions of years ago, so we're looking at 4,000 years, millions of years ago. This is just 4.5 billion. All right, so this is 4.5 billion. All right, we're starting here at the formation of the moon, the Hadean era. At about 4 billion years ago, we were bombarded with asteroids, comets, as the solar system was kind of finalizing its final place with the planets and accreting the different large rocks in space to the planets. So we were bombarded with asteroids and comets. Used to think this is where most of our water came from, but the elements and the types of oxygen and hydrogen used in our water, it doesn't match up with the water that's in the Oort cloud. So we're not entirely sure where our water has come from. All right, that was 4 billion years ago. The Archean period is where we start to have life. So first life after the heavy bombardment. Earliest start of photosynthesis is around 3 billion years ago. So 4 billion years ago we have life. 3 billion years ago we start photosynthesis. With photosynthesis, you can't have oxygen until you have photosynthesis. So we don't have advanced life until you get to the end of the Proterozoic, into the Cambrian explosion. So billions of years need to go on to build up oxygen. Earth actually becomes fully frozen due to its unstable tilt. It's finally achieving that 23.5-degree tilt. This happens a couple of times. Proterozoic period, and then the Paleozoic period is where you start to see animals on land. You start to see organisms in the oceans. A couple mass extinctions. Mesozoic is the beginning of the dinosaurs. And then the Cenozoic is our era right now. And if you look at this whole clock, there's humans right there. 2 million years ago. Or not even humans, but hominins. There, that little, you see it? That little nub? Oh, you don't see it? Here, let's keep zooming in. See that little brown nub right there? Yeah, that's humans. Compare that with the rest of the clock. That's how long we've been on this planet. Where do we get all the evidence that this has actually happened is through fossils and geological research of the layers of the Earth and the composition of the atmosphere when it's been trapped in ice for millions to billions of years. So pretty cool in that how long and the Earth has been involved in trying to build what we see today. Make your own transparent backgrounds. How people put your face on stuff. Great, yeah. I'll find a Photoshop browser app. Maybe I'll make a Newton cradle, just like they make my face. So that was just a little bit of information on the geological time periods, just to help your background as we do scratching the surface. Okay? So we're going to talk about the layers of the Earth, review what you did your research on your Explore section right here. I helped you do the inner core, set it up so that you could do the outer core, mantle, and crust. Sources just pasted into the box over there. You could use the same source. There was no limitations. All right. Nat Geo had some good information. The USGS, United States Geological Survey, geologists of the United States, they had a lot of good information too. I was just asking you to look for very basic information. Temperature, depth from the surface, so how far down, not the thickness, just how far down. Composition, state of matter, and other. So just kind of review a little bit. Here's our Earth. And in our Earth, we have a core at the center. Just like, think of like a pizza almost too. The center part's the core, the outer part, the edge. It's like a piece of bread or a piece of pizza. You have a crust. Okay? Well, there's two parts to the core. Almost looks like an eyeball here. We have an outer core and we have an inner core. So there's two cores. Well, one core, but a sublayer inside the core. Everywhere else in between is the mantle. So just from looking at this very simple diagram, very simple representation, what I can kind of see right now is the crust is the thinnest layer. The mantle is the largest in terms of volume. And there's two cores. There's an outer and there's an inner core. We'll go back here. We'll start with the inner core. Its temperature is around 5100 degrees Celsius. So over 5000 degrees Celsius, which is, I think hotter than the surface of the sun. Depth, but again, the sun's hottest location is the corona, the atmosphere. The depth from the surface, we go 5200 kilometers down. So depth from the surface, if you start at the crust, and you want to go right to the edge of the inner core, that's a terrible line. That depth is 5200 kilometers. I believe it's about 6,000 to get to the very center. Okay? That's 5200 kilometers down to the inner core. Temperature is about 5100 degrees Celsius. Its composition, if it's in the core, think of this as a massive density column, in that the most densest material is going to be at the bottom, and the lightest, least dense material will be at the top. Very few things are more denser than metal, so at the inner core, there is a lot of iron. A lot of iron, 5100 degrees Celsius, and this is a solid. Why is it a solid? I would kind of put that as the other. It's a solid because of the intense pressure. There's no space for the iron molecules to move into a liquid state. They're crushed in together. Intense pressure. If you remember back to the classroom where we had that syringe and you put the lock on and you pull it out, you let go, and then the syringe gets slammed back inside. Well, that's because of air pressure. About 15 pounds per square inch. That's a lot of pressure, believe it or not. So then you add the atmosphere, and then you add all these layers down to the inner core. You're looking at 3.6 million atmospheres. 3.6 times 15 pounds per square inch. Those iron atoms can't go anywhere. They get crushed in next to each other, like a bunch of kids trying to go to multi-B. And they stay in a solid state, even though they're incredibly, incredibly hot, hotter than the melting point for iron. They stay solid. Okay? Outer core, a little different. Outer core has iron, and nickel. A little less extreme. This is a liquid because there's not as much pressure as there is in the inner core. Okay. I think if we use, where was the USGS website. This is in reverse. There it is. 2,900 kilometers down. And it's a liquid. I left the outer core. Mantle. Obviously, it's the largest. You use the thickness of the crust, and you'll start in the mantle. So the mantle starts about 100 kilometers down from the crust. So from here to here is about 100 kilometers. Mantle is semi-molten. We say it's not completely a liquid. It's a solid, but it's a solid that convects, which means inside the mantle, and this is kind of like a special feature. This is like an other. This is something I would include for the other. Is that the mantle causes or has convection in that warmer material rises and then sinks. Warm rises and cool sinks. And in the extend section, there's kind of like a simulator, an interactive model that shows you the mantle convecting. So we have heat in the core due to pressure and due to radioactive elements producing radiation, adding heat to the material around the core, and those rocks and magma and other material will rise because it's less dense, it's warmer, and then as it loses thermal energy, it's not becoming colder, it's losing thermal energy, it'll contract, lose spacing, and sink. And so we have this convection happening inside the mantle. And the crust is very thin and made out of very brittle material, not made out of metal, made out of silicate, different oxide, minerals, rocks. That's very, very brittle compared to the metal inside the cores and the magma below. And so the crust breaks apart. So this convection is going to become incredibly important for what we talk about towards the end of this assignment, and that's plate tectonics. That the crust is actually subdivided and broken in different spots. And where you get convection currents that align, you start having these plates move away from each other. And that's where you get different boundaries. Alright, but that's kind of getting ahead of myself. I just wanted to briefly review the layers. You should have more information than I do. Temperature of the crust is basically the temperature of the atmosphere because you are out of the interior of the Earth. The mantle is varying, warmer at the bottom, cooler at the top. I would again use best information you can use from Nat Geo or the U.S. Geological Survey. Alright. I think this just talks about the cores. Yeah. I'd have to search up mantle and crust. Oh, this is in the extend section. mantle and crust on USGS, and it'll probably give me a very simple breakdown. Starts about 100 kilometers down. Various minerals, they don't give much information. Dense hot layer of semi-solid rock. So the composition you could just say is just semi-solid rock. And then give, yes, it has iron, magnesium, and calcium. But this is pretty much what the crust is going to, not including some iron, a lot of magnesium, calcium, oxygen, and silicon. Alright. Logan wants to know how many more assignments are left. He keeps asking Kildoff's meet. Well, he's asking the wrong person then. So, next on the agenda, answer the explain questions. So based on your research, based on what we discussed, go ahead and answering 1 through 4. Alright, and then you are stopping here for today, if you didn't already understand. Stop here for Tuesday, 5/26. What is pressure? What are 2 ways to increase it? Think back to 7th grade. So I will help you kind of think back to 7th grade. Anybody have a definition from 7th grade before I say it? Because that takes all the fun. A definition of pressure. The force on something. Yeah, it is something. I would just include that other word. You gotta be very specific with this definition. So it's the amount of force over a what? Over a given what? Over an object, over a specific surface. What's length times width? Yeah, no, that's very true. That's over an object is good, over a specific surface. I would include over a given area. So you could be an area of an object. Hey, there you go. No, not including height, area. So the pressure is the amount of force over a given area. And there's a reason why I'm being picky with area, because there's 2 ways to increase pressure. So think about what I just said. Pressure is the amount of force over area. So really, you can think of it as a formula. Pressure is equal to force divided by area. So you could add weight, right? And weight, another kind of formula, weight is equal to mass times gravity. And this comes from Einstein's version of force equals mass times acceleration. We use acceleration due to gravity to calculate your weight. So Now, you can't really change the density of something without chemically altering it. So you do mass times gravity. If you increase mass, not density, but if you increase the mass, you're going to bump force. So if you increase mass, you're going to increase force. And so force, increasing the force is going to make a larger dividend, right? Numerator divided by denominator, you need a larger number here, you need a smaller number here, right? So if I do 2 divided by 2, I get 1. Well, how do I make 1 greater? I could do 4 divided by 2, and then I'll get 2. So it's some math, right? If I, oops, I cannot tab over there. Think again about an example, right? Two divided by 2 is 1. If I make a larger numerator, if I go 4 divided by 2, then I get a larger dividend. I get a larger divisor, right? Larger answer. So I need to increase the top number of a fraction to make a larger number, so I can make force increase. If I make force increase, and I have more mass, then I'm going to increase pressure, okay? Area now, the opposite is true. If I make it smaller, I can make this number bigger, right? So let's use my example again. If I make this number smaller, so 1 is equal to 2 divided by 2. I can make this 2, I can make this 1. What's 2 divided by 1? It's 2. You see that? This is division. That is division, right? So force divided by area. I can either make force increase, or I can decrease the area. All right? Force. Well, I could put a rock on something and increase the pressure. Right? Increase the weight. Right? Area. I can make the area smaller and increase the pressure. What's a really good example of making the area smaller is a hammer and a nail. Right? Take a nail, smack it with a hammer, that nail is going to go through a lot of things. Why? Because the point of a nail makes a small area. That small area allows it to pierce through a lot of materials. Okay? Wood, plastic, so on and so forth. So nails work by this idea. Let's make the area small, come to a point which magnifies our pressure. You can punch a table and your fist isn't going to go through. With the same amount of force, you could take a hammer and bang a nail, and that nail will go through the table. Same amount of energy, but just because you made the area smaller on the tip of the nail is going to go through the table. So there's two ways to change pressure, to increase it. And this is to lead you into the rest of the questions. Okay, so what is pressure? Well, we defined it. What are two ways to increase it? You can either increase force or decrease area, and that is relating back to 7th grade. So the rest of these questions, so making the area smaller focuses the energy further. Yes, Nikolai. The rest of these questions kind of follow, well, what if you make mass greater, right? Because as you go down to the inner core, you are increasing the mass that is pressing on the layer below it. Alright? So the inner core has the most pressure. The outer core gets the second highest amount of pressure. The mantle gets the third highest amount of pressure. And the crust only has the atmosphere pressing down on it. I say only, but that's incredibly heavy. Okay? So if you could order them from greatest to least pressure, from greatest to least pressure, goes from inner core to outer core to mantle to crust. Okay? Which layer of the Earth experiences the greatest pressure? I think I addressed that. Which layer experiences the least? How do you know this? Refer to your research. So again, greatest to least, I just said it, would be, nope, inner core, mantle, crust. Let's zoom in a little bit. Okay, and you got to put those into sentences. I don't want to see notation. I'm doing this for speed, really, right now. Which layer increases the least? Layer experiences the least crust at the end of that. How do you know this? Go back to your previous answer. How do you know the inner core receives the most and the crust receives the least? How do you know? Because pressure is based on force. And also, you could also look at area. The core has a very small area. It's a very small layer. So all this pressure is pressing down on the very small core, which makes pressure magnify, focus even more, like Nikolai said, onto it. Okay? So again, small surface area, lot of mass, which means a lot of force. So a lot of force over a little area. Less force over a little larger area. Even less force over an even bigger area. And then very little force over an enormous area. So they kind of change over time, right? High force, low area, and then it kind of alternates as you move out to the crust. Alright, maybe I'll make a note of that, just so you guys have that available to yourself. What color should I use? So high force, low area. And the crust is low force. Oops, I don't want to do division. Well, I could do division. Low force over a high area. This makes a very low pressure. This makes a very high pressure. Okay? So using math to kind of understand why. It's one thing to be able to regurgitate to me and tell me in a sentence, hey, inner core's got more pressure, crust's got less pressure. Taking it to the next level is understanding why, and that's based on using Sir Isaac Newton's idea of force times mass over acceleration, and therefore that relating to pressure. Okay? If you can do that, you're doing really good. How does the pressure experienced by each layer relate to what state of matter that layer experiences? Why is the inner core a solid again? Why is the outer core a liquid? I think that will help you moving along. Intense pressure means intense energy, intense heat. Enough heat to turn the outer core liquid, but too much to make it a solid. How does density affect the composition of each of the layers? I shouldn't capitalize the elements. So, to get this question, how does density affect the composition of each layer of the Earth? You're going to go to ptable.com, and you're going to look for iron and nickel first. Interactive, very cool periodic table. Okay, iron's here at atomic number 26, nickel's over here at atomic number 28. Okay, mass correlates with density for our purposes today. Okay, higher the mass, the more dense these elements are going to be. You can even click on the element and you get a little bit of information from Wikipedia. All right, you can find face cam blocks on. Face cam goes away. You can find the density, and yes, you can use Wikipedia to find the density for iron at 7.8 grams per cubic centimeter. All right, density of nickel, 8.9 grams per cubic centimeter. Okay, those are at the center of the Earth. What about some of the other elements that are kind of in the mantle or in the crust? That would be, if I go back here, thinking about magnesium, calcium, silicon, and oxygen. So let's take a look at silicon and oxygen. Here's silicon, atomic number 14, its density, and this is a lot near the crust, 2.3 grams per cubic centimeter. Remember, iron was about, I think, 7, nickel's about 8, right? This is 2 grams per cubic centimeter. Oxygen, its density, and this is liquid oxygen, 1.4. Kind of relationship do you see between the layers and density? So describe the relationship. The deeper you go, what happens to density? And this kind of goes back to last year. Think of the Earth as a three-dimensional density column. You know, you take corn syrup, you take water, you take vegetable oil, you take, I don't know what else you might have used. You pour them in a graduated cylinder, and then they separate into layers. Remember doing that last year, maybe? Hopefully. I know Miss Simus does it. The Earth is a three-dimensional density column. It's a density column in all directions. Okay? Due to gravity separating the layers, gravity works in all directions, not just down. Okay? We talked about that. They work in all directions. That's why we have spheres in space. We don't have cubes. We don't have flat Earths. We have spheres. Because gravity works in all directions. And if gravity works in all directions, the denser, heavier elements are going to go to the center of the Earth. Yes, we have iron in the core, in the crust. We have gold in the crust. Right? We have platinum. We have these elements in the crust. However, these elements are trapped in other rock, which aren't as dense. And that's where we get ore from. Iron ore, copper ore, right? Gold ore. Ore is these elements mixed in with other rock and other material. You need to melt the ore down to separate the metal from the rock. And then you refine by taking the pure metal and then let it set again. And then there you go. Now you have your gold. So the gold and the iron and the nickel and the platinum and the palladium, all those rare metals, all those valuable metals, silver, right? These denser, rarer metals, there's a lot of it down in the interior of the Earth. It's just when the Earth was forming, some of this metal got trapped in these convection currents when the Earth finally settled as a density column, and that became the ore that we refine today. There is a lot of uranium down in near the center of the Earth, highly radioactive. Okay, it's refined now for nuclear fuel and unfortunately weapons, and enriched for a certain isotope, but there's a lot of this down near the core and the lower mantle of the Earth, and it provides a lot of heat for the Earth. You need the heat, you need the energy to power convection in the mantle. Because if you don't have convection in the mantle, you have a dead Earth. No magnetic field, no plate tectonics. Okay? So a little extra information here and there, but again, designed to help you add detail to your answers. Not just one and done answers. Being able to understand a little further. Okay? All you are doing today is the explain section. That's it. We will save the extend for tomorrow. And the extend section, disclaimer, is long, but it's because we have this to talk about. The mantle's so large that there is convection happening inside of it. And so tomorrow we'll briefly take a look at this. The outer core, the mantle, what happens when you add heat, or you take thermal energy away, or you cause an earthquake. Where do those waves go? It's a pretty cool and mesmerizing sim, but we'll get there tomorrow. We need good background information on this, especially this density question, because this density question will help us explain how scientists were able to figure out the layers. Their type, their composition, why there's 4, why isn't there 8, okay? Are there any questions? No? If you have questions while you're working on the questions, later today, send a message through email, reminds, and I'll answer when I can. Obviously, hopefully this gave you a good direction to go on. This should have been done already last week. This explain section, what we're doing today. The extend section, if you want a little preview, you can look ahead. Requires using the simulator, a couple questions on that. Describing what happens during an earthquake. So there's 6 questions in the extend. We're using the model, and so a lot of the time we'll be focusing on that. There's no DNA, so again, it's just all the extend section. Alright? But the trade-off is there's only 3 evaluate. And then that's it for scratching the surface. We'll turn this in Thursday before midnight. Friday is an ACK Lab day. I don't think there will be a Mighty Meetup again because most of June will be ACK Lab days and Meetup days. So we'll have a bunch of Meetup days in June. Alright? So right now it's a focus of getting our work done, any missing work done, any revisions done. Really within that first week of June. Alright? This Thursday is locker pickup. If you have things that you left in your locker on March 13th, you want them back, you gotta come to the school. Email was sent to your parents to pick your things up. If probably the less amount of people that go, the better. But if they are going, you need to adhere to social distancing rules, masks, 6 feet apart. Things will be bagged up. Obviously, they were, sanitized prior to being bagged up. And then you can have your things back. There is a night pickup too that Thursday, the 28th. And then if you don't pick it up, it gets donated. So make sure you pick your things up, or you make an appointment. See you, Nikolai. So if you guys got no other questions, I'll see you guys later. Again, you're just doing the explain. If you want to start looking at the simulator, you can do that, but you don't have to answer any questions. Alright? Hi, Azra. Hi, Hike. Hi, Charlie. See you, Rainy. Hi, Logan. Bye, Ava. How dare you?